All right, so today we are going over a couple different things. So again, our calendar. I did change some things around. This calendar is a little old, but again, density was originally supposed to be done on Wednesday. I pushed that over to the same day as similar solids. So what we're doing today is three things. We're doing density, which also includes displacement, and then similar solids, which includes things like scale factor, area ratios, and volume ratios. So those are the things that we're covering today. Now, again, all of the stuff that we're covering today, they're important topics. However, we are going to leave them off of the next test. The assignment today, again, we'll use some review from the previous ideas of volume, and then it's also going to do the new ideas of area, scale factor, density, things like that. So next week, we're going to be doing all review stuff leading up to our test, which will be opened on Thursday. And that'll be our last test. So this is actually our last section where we're doing any new material for the year. All the other sections that we have next week will be review. And then I had also posted a calendar for the last 2 weeks of school. Essentially, on the last 2 weeks, we're going to be doing some algebra practice on the week after the test. I'll also have a window for makeup test, just like I did the last time. And then the last week, I'm not going to post anything new at all. So for today, again, we're still going to be using a lot of the formulas that we've done before. Again, anything on this sheet couldn't apply to this section, so it's important to have that as a reference. But there are some other formulas. So this page is actually a summary of everything that I'm going to go over today. So the main ideas here are density, displacement, and similar solids. So again, if you want to, this page would be a good page to print off as another resource for when you're taking your test. So again, it kind of summarizes all the other equations for today's section. Oh, sorry, I forgot. I'm not including this on the test. Ignore that. If we were having a test on this, this would be a nice summary to print off. But again, it won't be on the test. But while you're doing your assignment for this section, it would be a good thing to have with you as you're working on your assignment. All right, first thing that we're going to talk about is density. Now, we've talked about density a couple times, but every time we've talked about density so far, it's been in terms of things like population density, or even in the last section, there was a little bit about population density. So the density that we're talking about now is actual density, where we're looking at mass over volume. So we've talked about how to find volume. Mass, we're talking about weight. So density is just taking the mass or the weight of an object and putting it over the volume, the amount of space it takes up. So we have 2 example questions here, and the notes are kind of shorter for today. I think they're only maybe like 9 slides total. So we've already done like 3 or 4 just on the intro stuff. So it's going to be a very short lesson. Now, for the first question, it says, James Marshall found a shiny metal object in Sutter's Mill. If the metal had a volume of 259 centimeters cubic, then how much did it weigh to the nearest gram? And if it says if it was pure gold. So I'm giving you also the density of pure gold. So we're going to find out if, or what it should have weighed if it was pure gold. So we have our density is given to us. We have the mass is not, that's what we're trying to find, and the volume is also given to us. So the things that we have, oops, this is our volume, and this is our density. So we're going to plug into this formula here. So we have 19.3 equals the mass, which is what we're trying to find, over the volume, which is 259. Now, just to refresh memories on density, some people learn density like this. They did D equals a heart, and then they drew a line through it. So it's mass over volume. Again, easy way to remember that formula. It'll come up more in science classes as well. But we have a little bit of algebra to do here. So let me grab a calc there. All we actually have to do to solve this problem, we gotta get the volume over to the other side. So we need to multiply it off. So we're gonna multiply both sides by that 259. Get over to the other side. So it's gonna cancel off here. And we're gonna have 19.3 times 259. And it gives us 4998.7. So this would be the weight if it was pure gold. Whoops, not centimeters. Scratch that. Grams. That was supposed to be a cursive G, but anyway, grams. So if you was to weigh it and it weighed that much, well then it must be pure gold. All right. The next one, Mr. Midas loves gold. He even had a 14-karat gold paperweight in the shape of a cone. Find the density of the paperweight to the nearest hundredth if the cone had the dimensions listed and a weight of 9.3 pounds. Now, there's different ways that you can measure gold. So on this one, we're talking about 14-karat gold. Again, if you know anything about gold, there's lots of different ways that you can talk about gold. So I forget, I think pure gold is, I forget, I think it's 24-karat gold, maybe is pure gold, I forget. But again, for different types of gold, based on the carats, that would be different types of density. So let's take a look at this problem. We have the weight, and we have our cone, and they gave us some dimensions. So they didn't give us a volume, but they want us to find density. So what do we have to do? We have to find the volume first on this problem. So we got to go back and use one of our formulas from the earlier section. So for a cone, our formula is 1/3. 1/3. The base area times the height. That was our basic formula for a cone. Again, starting off basic. But then for a cone, the bottom's always a circle, so we could plug in the formula for area of a circle, which is pi r squared. And that's the formula I'm going to use right now. So let's go ahead and plug in. We have 1/3. We have a radius, but they didn't give us a radius. They gave us the diameter, so we got to know, all right, this piece is actually 6. That's going to be a radius. So pi 6 squared. Oh, and so this was diameter. This was radius. This is our slant height. That's not our height. We need our height, which is over here. So again, we got to do some math in order to solve for our height. Well, again, we have a right triangle, and this is a right triangle that takes the shape of one of our Pythagorean triples. This is our 3, 4, 5. That's been doubled, 6, 8, 10. So the missing dimension here, the height, should be 8. So we're going to plug that in, and then we can solve this problem. Again, if you don't know your triples, you should. So 6 squared, that's going to be 36. So I have 1/3 times 36 times 8. Let's multiply that out. We got 1/3 of 36 is going to be 12. So that's 12 times 8, which is 96. So this is 96 pi. Now we're going to be figuring out density in a minute, so we want to actually get a decimal here. So let's do 96 times 3.14. So the volume of this is 301.44. And again, this was in centimeters cubic. So on this problem, we have our volume. They gave us, in the original problem, they gave us the weight. So now we can finally plug into our density equation. So let me change the color for this next step. So now we're going to go ahead and take our equation, density equals mass over volume. So we're going to plug in the mass and the volume that we had and just divide. So 9.3 over 301.44. So we have 9.3 divided by 344, and we get wait. Compound. Yep, okay. So 0.30085, bunch of other decimals. So didn't say what to round to, I don't think, did I? Oh, hundredths place. All right. So for our final answer, if we're doing this, 0.03, and this was in, what were our dimensions? This time it is pounds. So pounds per cubic centimeter. Again, notice, wasn't the same as this one up here because this is in grams per cubic centimeter. So they gave us different dimensions. And we're just going to leave them in the dimensions that they gave us. It didn't say to change them to anything else. So we're going to leave it like that. All right, let's go on to the next one. So now displacement. So displacement, displacement. What is going on here? My pen has a mind of its own. All right, try that again. All right, for displacement, I wrote two equations down here. Essentially, anytime we're looking at displacement, we're going to have some type of container, and we're trying to find the volume of an object, some irregular shaped object. And when we place that object in the container, that container will be filled with something. It could be some type of liquid in most cases. And when you place the object in, it'll make the volume rise. So in this example, we have ourselves a fish tank. And you'll see in this fish tank, I got these two fish in this castle. So let's go ahead and read the problem. It says the fish tank has a base that is 30 inches by 15 inches. All right, so let me go ahead and write down the important information here. This is 30 by 15. Again, they're in inches. And a height of 22 inches. So this entire height is 22 inches. All right, then it says, with only one fish, the castle in the tank, the water level is at 16 inches. All right. So originally the water height was at 16 inches. When the second fish is added in, the water level rises to 17.5 inches. What is the cubic volume of the second fish? So if we look at this, so right now there's two fish in the tank. So this height was 17.5. But it's also saying that before the height was here, and this height would have been 16 inches. Now, some of this information is not needed. Out of all the information, the one thing that's not needed at all is the height of the fish tank. I don't care about how much volume that fish tank can hold. It has nothing to do with the actual problem. What we need to look at is the change in the level of the liquid. So there's two ways to look at this. Now, it really depends on the shape that you have. This is a nice rectangular prism, so there's an easier way to do this problem than to do the first formula. The first formula is for any type of container. So it doesn't matter if it's a prism, a cone, a pyramid, whatever. If you take the volume of the water that's in the container before you place the object in it, and then you subtract that from the volume when there's the object in it, that's going to give you the overall change in volume. So that's what this represents. Again, this is actually a delta symbol. So in this, we're using it as change. So change of volume of the liquid is what you'd be finding in order to find the volume of the object. Well, in most of these cases, we're going to go with something easy. We're going to go with some type of prism or cylinder. It's much easier to do displacement with those two types of containers, because all you actually have to look for, instead of finding the overall volume of the entire water, both before and after, you actually only have to do the volume of what's been displaced. So in order to do that, the shape of the container, when it's a prism or cylinder, is still going to be the same shape for the displaced water. So if you look at just, let's imagine I had this line go all the way across, and I also had it follow along the back here. If you look at the shape that's created with this red line and the top part of the water there, that too is a rectangular prism, because it maintains the shape of the base the entire way up. And then we have, again, two bases that are the same size, that are in parallel planes. And it's also going to have the height here will actually be the height of displacement. That's what we're really using. So that change in height of the liquid is the height that we would use to find this. So we don't have to find the overall volume of the water at all. It's just what's been displaced. And that'll give you the volume of the fish in this case. So we know that the height before the second fish was put in was 16. The height after was 17.5. So first thing we're going to do is take the 17.5, subtract off the 16, and that gives us 1.5. This is the change in height for this problem. So the water is making a prism with a height of 1.5. So now we can take that and plug it into our formula. Well, our base is a rectangle, so we have 30 by 15. So using our formula, we're going to take the base. We have the volume, sorry, the height of the liquid, the change of it was 1.5. For the base, we're going to go ahead and plug in those two dimensions, 30 times 15. So now 30 times 15, that's going to be 450. And then multiply that by 1.5. What's that going to be? 450 times 1.5 is 675. And this is, we're talking about cubic inches, because all these dimensions were in inches. So this is a volume measure, so it should be in units cubed. So that would be our answer. Now that's a really big fish, much bigger than what I have pictured there. So again, diagram might not be drawn to scale, right, but that's how you find it. So again, if you want to find the shape of some sort of irregular object, you can place it in water that's in a container and see how much did it rise by, and then use that formula to calculate what the actual volume is. And that's how, if you go back to the first problem, let's go back for a second. When we're doing density, when we're talking about somebody found a piece of gold, well, gold is a very irregular shape. So if we wanted to keep going with this idea of gold, if you didn't know the volume, because again, how does he know the volume? Well, you'd have to actually place it in water to see how much did the water rise, calculate that volume, and then you'd be able to take that, put it over its weight, or sorry, the mass over the volume, and then find out the density. So again, there's always a way to find the volume if you have a container that you could submerge it in. All right, let's go ahead and go to the last one. All right, similar solids. So we did a section earlier in the year on similarity when it came to two-dimensional figures. And we talked about the image and the pre-image. and we did a lot with transformations. We had also at the same time talked about different type of transformations that didn't change the size compared to transformations that did change the size. And we talked about a dilation. Well, you can also dilate a three-dimensional image as well. We're not doing this on a coordinate plane like we did the last time. The only thing that we're going to talk about here is how the original pre-image is related to an image if it is similar. Now, in order to have similar solids, it still fits the same criteria as similar figures before. You have to have proportional sides, and you have to have all the same angle measures. So we still have the same main idea when it comes to doing similar solids as we did with similar figures. And just like we did before, K a lot of times represents our scale factor. So a lot of times you'll see me abbreviate scale factor as either SF or as K. And when we talked about scale factor before, scale factor applies to any single dimensional measurement. So if we're looking at the two cubes here, the first one up top is the pre-image. The second one is the image. So this has been enlarged, it's getting bigger. So if I take the sides, I have 1 cubic centimeter for the original image and 5 cubic centimeters for the image, and place them over top of each other. Again, it's always pre-image on top. Sorry, image on top, pre-image on bottom. Because again, if it's getting bigger, the bigger number is going to be on top. If it was getting smaller, say it was a reduction, then the smaller number should be on top, because your scale factor should be greater than 1 for an enlargement and less than 1 for a reduction. So in this case, we have the 5 from the image over the 1 from the pre-image. Now, what happens as you look at the area of any of these pieces? So let's say we looked at the area of just the base. All right, so we could consider the top of the base here. Well, this is a 5 by 5 square. So if I did 5 by 5, that'd be 25. Up here, 1 by 1 is still just 1. So here we have 25 to 1. Well, how did we get that 25 to 1 ratio? Well, what actually happened is we took that value and we squared it. So let me get rid of this writing here so I can show what I have hiding. So again, we have that value. We essentially square that value to get this. So this relates right back to the original numbers. If we're looking at this as A over B, whatever numbers we're plugging in for the scale factor, the area ratio is going to be those values squared. So if we're looking at it just in terms of K, again, whatever the K value is, whatever that scale factor is, it's going to be squared when we talk about it in terms of an area ratio. And we're going to look at another problem dealing with this in a second to see how this would apply. The next thing that we need to talk about, though, is volume. So volume. If we then went one more step here, and instead of just looking at one of the sides, we looked at the entire volume of this, well, then we'd be doing area of the base times the height. Well, we found the area of the base, and the height here is 5. So for this one, we'd be taking, base times height. So 25 times 5, which is 125. Again, we just found volume. So same thing up here for volume. Again, base area times height, which again, this value that we got here was for base area. Same thing down here. So plug it in, 1, and then the height on this one was also 1, so it's over 1. And we have 125 for our image volume and 1 for the pre-images volume. Well, how did that relate? Again, go back to the idea of we had 25 before, right? And we had 5 originally. Well, 25 times 5 is 125. So essentially we did 5 times 5 times 5, or 5 cubed. And this will apply every single time we talk about volume of similar images. So whatever our scale factor is, oh, there's a typo. Couldn't get through notes without one typo. So that would be 3. So we have k to the third, and that means that that typo must also be on that first page. So let me go back real fast before and I'll repost the notes with the corrected value. But yep, there it is. I made the same typo right here. Fix that. And I will repost it. But again, that should be a cube because we're doing 3 dimensions. All right, back to where we were. All right, again, this applies for any type of solid. So your scale factor will apply to any single dimensional measurement. So that can be height, that can be width, it could be length, it could be slant height, it could be perimeter, anything that you measure in single units, it's going to be using scale factor. Anything that's doing area, so whether it's area of the base, lateral area, surface area, those things will all use the ratio for the area ratio. And then volume, again, that would use the volume ratio. So let's see how we could use this to find different things. So in the first one here, it says the ratio of the heights of a pair of similar cones is 3:2. What's the ratio of the volume? So if you knew how the sides compared, you'd be able to take that value and apply it to to the volume. So in this case, you're going to take both those numbers and cube them. So we have 3/2 cubed, because now we're talking about volume. So this is going to give us 9. Oops, no, not 9. That's only squared. 27. 27. Let me erase that. 3 times 3 times 3 is 27. And then 2 times 2 times 2 is 8. So 27/8. This would be the ratio of our volumes. So let's say we knew what the figure was, all right? And we said that we knew what the volume was. Well, then we can take that volume ratio and figure out the volume of the other figure without knowing all of the dimensions. And then you take a proportion, you set a proportion using your new volume ratio. Again, I'm not trying to go into too much detail here because I'm not going to put this on the test. All right. But again, it's good to know. The last one there, the ratio of the surface areas of 2 similar cones is 36/64. What's the ratio of their bases? So if they told you what the ratio of their surface area was, or any area, then you should be able to go backwards and find your scale factor. So if I wanted to know, or actually in this case, we don't have to do any work on this, because if we notice, surface area is what they're giving us. So ratio of the surface area, they want ratio of the bases. On this one, it's going to be the same thing, 36/64. That's our answer. It's the same thing because both of these are in square units, so it remains the same. Now, if they had asked us for a ratio, either our scale factor or our volume ratio, we could find either one of those. So let me set up a chart here. Again, this is not what the question is asking, but this is what we could do if we needed either our scale factor or our volume ratio in this problem. We know that this middle one is 36/64. Well, we could take that, and in order to go backwards, instead of squaring it, we'd have to do the square root. So 36/64, oops, 64. Square root of 36 is 6. Square root of 64 is 8. And if we wanted our volume ratio, we'd take these original numbers from our scale factor, and we'd have to cube them. So you'd have to do 6 cubed or 8 cubed. Now, something else I just realized is that these numbers could have been reduced. That's fine. If you wanted to reduce these, we could have. This would have been reduced by 2. This would have been 3 and 4. So notice all these things are still the same though, because if I squared these numbers, I'd also get 9 over 16, which I could have divided both of these by 4 and got 9 over 16. Before I cube this, let's go ahead and change them. If this was 3 and 4 instead. 3 to the third power is 27. 4 to the third power is 64. And that'd be our answer. All right, that's it for this section. There is an assignment that goes along with this, and I'm going to post it on Edsby here in a few minutes, but this is the worksheet that I'm having you guys do. There's a little review of some volume stuff, and then also in here there's density, displacement, and similar solids. So again, I'm not going to ask you the density, displacement, and similar solid stuff on the test. The test will focus mainly on what we've covered the last few weeks on surface area, lateral area, and volume. I'll also be posting at the beginning of next week a couple of different reviews. You already know that one of the reviews is coming from your textbook, like always. So you'll have that review. But then there's another review that I'm going to be posting for when we go over it on Wednesday in class. So on Monday, we'll be looking at the textbook review. And on Wednesday, we'll be looking at the worksheet review. Are there any questions? I didn't see anybody post anything in chat today. All right, well, again, keep working. You guys are doing good. There's only a few people that don't have passing grades right now, so make sure you keep turning stuff in. Also, after the end of next week, after you finish that test, whatever you have after I put in the grades for that test, that will essentially be the lowest thing that you could get for a final grade. Because then the following week, I'll be doing those worksheets for algebra review. But for those worksheets, they're going to be extra credit as well. So again, after the next test, your grades won't go down anymore after that. So again, make sure you keep working hard, finish strong, try to shoot for an A or B this semester. Again, keep your GPA high. All right. And again, I'll be back on Monday to go over the review from the textbook. And then on Wednesday, I'll be on to go over the review worksheet that I'm going to be posting. All right. Have a good one.